Okay. So move to 7.4, second order. And I mean, it's a special order. First order might be too simple, and second order may be slightly more difficult and more general. But then, as it turns out, at least some of these second order differential equations are very common. We'll use that in other contexts, like especially in solving partial differential equation that are commonly used in physics, like solve Laplace equation or that Helmholtz equation. The reason is that most of those equations that we saw in at least the simple context in physics, like E and M, or that even the quantum mechanics, the Schrodinger equation, they were second order in space, right? And then when you use different coordinate system, the second order PDE, partial differential equation, becomes, you can separate that into ODE in different coordinates. So you commonly encounter second order ODE, because when you separate that into different equation, depends on different coordinate. Yeah, those becomes ODE. Right. So this ODE, some of these ODE are fairly common. So pay particular attention to that. And then some of those equations is the solution of some of these equations are very commonly used function. Like the Bessel equation, the solution would be Bessel function that very commonly used, and also the Legendre equation, the solution will be the Legendre polynomial or the Legendre function that we'll also cover later. So very very useful second order linear ODE. Right? And so the first part in this section is mainly about the classification of singularity, and which is useful later on in determining that whether the method that we will later talk about will be will work or not. So in 7.5 we'll talk about the series solution. The series is taking expansion about certain points, and the common idea is that if the point that you try to expand is nothing special, is what you call the ordinary point, and you always work. And then when it's singular, then there's degree of singularity. If some of them are more serious than others, so they're regular singularity, and then irregular. The irregular one, the series method may not work. In many cases, didn't work. Right. So that therefore you have this discussion first. I mean, at first it's just like trivial mathematical classification, but then the motivation is that they are useful when you try to determine about which point you want to do the expansion to find series solution. Okay, so now the idea is to write the general form. Now is this is y double pi. Y double pi is the second derivative, e square y dx square, and then plus p x dxy pi and plus q x y. And we stay with a homogeneous equation, right? And the inhomogeneous one, like I mentioned, we'll talk about that in another section. Okay. And now this P and Q again changed the definition different from what we did in a few different contexts that previously. So it's just arbitrary function of P and Q, right? And Now, this discussion of singularity is that when you have a singularity, it's when P and Q becomes infinity. When it's singular, then it's called singularity. If it's not singular, then it's ordinary. Right? So that's quite trivial. Right. So if so singularity is either Px, and you have two functions, right? So it's either if one of them singular, then we call that the singularity E. So P x0 or Q x0 goes to infinity as goes to x sub 0. That's the singularity. Singular. Right? That's trivial, right? And now for singularity, then you separate that into two parts. So for regular, so regular is Px, when you x minus x of 0 times P or actually you need n x minus x0 square is finite as x. If it's finite, then it's regular, right? If so, it's singular. P and Q's are singular, but if you multiply by one factor of P and one factor x minus x of 0 to P, that make it finite. Or I mean, and you both of them. So if one of them are violated, this becomes irregular. And then for Q, you multiply x minus x of 0 square. And if that make it finite, that is regular. So the regular, you need both of them. So it means that for irregular, it's either this is still singular or this is still singular, right? So that is the classification. Is that okay? So it's pretty straightforward, right? And there's not much to about that except the one special case or the at the point at x tends to infinity, right? If you want to see x0, if x0 equals to infinity, so what to do is this is I mean, this kind of way it doesn't work because you don't have a specific number for x sub 0 now. X sub 0 is just infinity. So what you do is set your transformation. I think it's C is 1 over x, right? And then do the transformation. And then this, I mean, you don't have to rename it. I mean, your text will rename this. It really depends on z. This is y. It depends on x. But then x becomes 1 over z. Right. Okay. You can still keep y because it's right. I mean, it's different function if you put it this way. Anyway, what we need to do is just transform the equation that depends on x to depends on z and write it again back to this form. So you have a different coefficient in the first derivative term and the linear term, right? So what you need to do is transform the derivative. So the dy dx becomes just the y, or change y to w, dw, dc, right? And then dz dx. which is dz dx is minus 1 over x squared. Right. dw dz. Right. But then this 1 over x squared go back to the c, this e squared, dw dz. Okay. Now you need the second derivative also. X squared. This will be this derivative over z and multiplied by dw dz, I mean dx dz, which again is this one is just minus c squared. Right. That is write it out explicitly, minus c squared is dz. I mean, there's two terms here. There's inside, yeah. I'll take the minus already, so it's 2z dw dz c squared b squared w dc squared. So now you substitute this one in here, this one in there. Okay. Oh yeah, you have another minus. Yeah, plus. Okay, so that is okay. So put it back to here, which is exactly this one. So d square y dx squared plus b dy dx equals to this one. The 2 times 2 zq dw dz that's c to the 4th power squared w dz squared plus p is actually minus d squared dw dz plus u. Well, now you just need to, that equals to 0. Or qw, that equals to 0. Okay, so you want to put it back to this form so you get the second derivative term, but you have the coefficient. You need to divide the C4 throughout the equation, assuming you don't have this zero term. But we will consider zero term, but z equals 0 actually is at infinity. So we look at what the behavior is z equals 0, but you divide it by C4, assuming it's not exactly 0. You can divide that. So yeah, d squared w dc squared. And then the linear term, combine this and that, and divide it by z to the 4th power plus 2 over z, right? And minus p over d squared dw dz. And then plus q. Q, right? Q over c squared, c4. Okay. And so, yeah, that's right. So now this becomes your new p, or you can call it p prime. This is the new q is p prime. That depends on z, and then you just use the same classification. Same way to look at that, whether it is regular or irregular, or ordinary, right? So that's the only trick. Now that might be involve a little bit. Right? It's okay. So that's the discussion. We won't do the singular point that much later, but just keep in mind that when you see an equation, where are the singularity, then look, just pay a little attention. If you get close to a singular point, you see whether your solution get into trouble.